decay and kind of tie this stuff together in terms of what goes on a larger level. So this is a little bit of review, guys. We talked about what makes an isotope stable versus unstable, and in the smaller nuclei, a small nucleus will tend to be stable if the number of protons and the number of neutrons are equal. Okay. Once the nuclei start getting larger, and again, this is just review, we've talked about this before, you start needing a little more neutrons to kind of offset the additional electromagnetic or electric repulsion of all the protons. So the additional neutrons add more strong nuclear force to the nucleus and tend to kind of hold it together. So for larger nuclei, you tend to have more neutrons than protons. And I don't know that there's a perfect balance, but there is kind of a nice equilibrium point where you have the right number of neutrons and the right number of protons, and that nucleus is happy and it's pretty stable. If you end up having too many neutrons or too few neutrons, then that nucleus will be unstable and it will decay to something else that will eventually be more stable. And that's kind of on a real abstract explanation of why nuclei go through radioactive decay and become other things, why some are stable and why some are not. Let me show you a graph of what we're talking about. We saw this graph before. Looks kind of like that. Every little red dot is a stable isotope. It's a stable nuclide. And notice that when we're down here in the small ones, the ones that are stable are the ones that have equal neutrons and protons. As we move into the larger elements, you start getting more neutrons than protons in order to have stability. All right? We've been talking about radioactive decay individually, alpha, beta, and gamma decay, and what happens to a parent nucleus when it undergoes decay and the products that happen. But the reality is radioactive elements don't usually just go through one thing. An element will decay to something else, and that thing that it has decayed to is also unstable, so it will decay, and so on and so on and so on. So it becomes a series of radioactive decays, usually, and that's what we call a decay series. When an isotope decays into another isotope that's also radioactive, then the process will continue. It's kind of like an avalanche almost. And this is one of the reasons why we can find some isotopes in nature that normally, just probably wouldn't be there, because you have this parent product that will decay into it. Bless you. And, as some things will decay, they go away, but then something else can be decaying into it, and it can then be there. So let's look at what a decay series might look like. Okay? Let's start with uranium-238, way up in the upper right-hand corner. Notice that anytime we have a red arrow here, we are losing 2 protons and 2 neutrons, and so that would be an alpha decay. On this chart, red arrow is alpha decay. A green arrow, we're gaining a proton, but we're staying at the same mass number, so that would be beta decay. So the numbers here on the y-axis that's the atomic mass, and the numbers on the x-axis are the atomic number. So notice uranium-238 will decay into thorium-234. It does that, and it has a very long half-life. It's hard for you to see this, but it's 4.5 billion years. We're going to talk about half-life in just a little bit. But uranium-238 is, yes, it decays, but it doesn't do it real fast. I mean, if you have a sample of it, it's going to take 4.5 billion years before half of it has decayed. When it becomes thorium, that thorium is more unstable. And with a half-life of 24 days, it will decay into palladium? Palladium-234, which then will decay into uranium-234 with a half-life of 6.7 hours. So it goes from 238 to thorium to palladium, now you're back to uranium again. We're back to uranium, but it's a different isotope of uranium. Now it's uranium-234, which will decay into thorium again, but now it's thorium-230, which goes to radium, to radon, to polonium. And then look, you get down here to polonium-218, and you have options. Polonium can go beta or alpha. It goes either way, and then and ultimately, see, so that's a decay series, okay? Let's talk a little bit about half-life and rate of decay, okay? The idea of radioactive decay, first of all, you need to understand, is a completely random process. You cannot predict. If I have one atom of uranium-238, I have absolutely no way of knowing when it's going to decay. It's just going to do it sometime, and it's going to do it whenever it wants to. It might decay right now. It might wait 4.5 billion years. It might wait 9 or 20 or 50 billion years. It's random, completely random. But if you have a large enough sample of material, and when we're talking on nuclei, we can, a kilogram of some element is a huge number of nuclei. With a large enough sample, you start getting statistically significant information that allows you to figure out, on average, what's going to happen. So when things decay, it's an exponential process. And you can look at it two ways. You can look at, okay, I have an original number of nuclei, the parent nuclei, I have an original amount. That amount will decrease in an exponential rate. What's connected to that is also how many decays are happening per second, what we call the activity, okay? The number of decays per second will also decrease exponentially with time. And that makes sense because if you think about, the number of decays per second is going to be proportional to the number of nuclei that you have. So both of those will decrease exponentially. And the idea of half-life, basically, the idea of half-life is the time it would take for half of the original nuclei to decay into something else. That's one way of looking at half-life. How long would it take for half of my nuclei to decay if I have a sample of this? Or how long would it take for the activity to decrease by 50%? So I have a certain number of decays per second happening. How long would it take for that rate to be 50% less? That would be the half-life. Or if I have one nucleus of this stuff, how long would it take before I would have a 50% chance of that thing decaying? That's probably the least common definition of half-life. The most common definition of half-life is the time it takes for half of the parent isotopes to decay, or the time it takes for the activity to decrease by half. Graphically, here's what radioactive decay looks like. That's an exponential function, exponential decay. Hopefully you guys have studied this in math. You can look at half-life in two different ways. Here is the number of parent nuclei. You start with a certain amount of whatever it is that's radioactive, and after a certain amount of time, you will have half of it. That's the half-life. After another half-life, you will have half of that, which is 1/4 of the original. And then one more half-life, you'll have half of that, which is 1/8 of the original, and so on and so on and so on, okay? This happens to be a graph, since this half-life is 5,730 years. This is the graph for carbon-14, which is a radioactive element. Carbon-14, really important in the world of science because it allows us to date things that are relatively young, as long as it was a carbon-based thing that we're trying to date. Like is it abundant? So the first graph, you guys, explaining half-life is talking about the number of parent nuclei. The second graph, which looks identical because it's the same idea, you can, instead of looking at the number of parent nuclei, you can look at the number of decays per second, and we call that activity. The number of decays per second is called activity, and that will also diminish exponentially, and it will follow the same curve, because really the activity that you have radioactively is proportional to the number of nuclei that you have. So they'll follow the same thing. Okay. Decay constant. Great. The decay constant, represented by the Greek letter lambda, which also sometimes means wavelength, but we're not talking about wavelength right now. We're talking about decay constants, okay? It is the ratio between the number of nuclei decaying per unit time and the total number that you originally had. So it's this ratio. It's the rate of, here's this delta N over delta T. It's the number of nuclei that are decaying per second divided by what you had, how many you had to start with. And really what that's telling you is how radioactive the substance is. A larger decay constant means this thing is less stable. It decays much more rapidly. So it's just a constant that tells you something about a particular element, and it is the ratio, bless you, of the rate of decay over the number that you had. And the activity of a sample, okay, is just the rate of decay. The number of nuclei that are decaying per second is called the activity. You can find it by taking the decay constant times the number of parent nuclei that you have. That will tell you the activity. So you'll get more activity if you have more of the substance, and you'll get more activity if that substance is more unstable, has a larger decay constant.
Hold on, let's let Tanner tell the national lecture. Yeah, that's it.
So here's the equation. This is known as the radioactive decay law. There's your equation, okay? It's got a base E to these power, to these exponents. And basically what it says is, if you want to know the number of nuclei that you have after a certain time period, you need to know the number you started with, you need to know this number E, and then you raise that to the negative lambda teeth power, okay? There you go. Recognize that N can either be the number of nuclei you end up with, or it can also be activity. So these N's can stand for the number or the activity, okay? And the sub-zero means the original amount, so the first N is what you're looking for after some time period, okay? So this is an equation that allows you to calculate either the activity or the number of daughter elements or nuclei you'll have after a certain time period. So a unit that you'll sometimes come across in this unit is called the becquerel. And the becquerel is a unit that measures activity. And an event per second, or one decay per second, would be an activity of 1 becquerel. Okay? It's usually probably going to be pretty big, depending on what you have. So, okay, doing some algebraic and logarithmic stuff, you end up with this next equation, which allows you to calculate the half-life of a substance. So, if you know the decay constant of a substance, you can find its half-life, or vice versa. The half-life is equal to the ln2, natural log of 2, divided by the decay constant. So these are the two equations that you'll be dealing with in terms of radioactive decay. These are the two main ones. You'll find both of them in your data booklet. If you're doing standard level work, you don't need to do it. If you're doing higher level work, this is in the higher level section. So but in this class, everyone has to know how to do it. I'm just talking about for the exam, okay? But in this class, we'll all be dealing with it, okay? You don't need to know how we did this. I just wanted you to show that came from somewhere. It wasn't just made up, okay? Okay. Radioactive dating, my favorite kind of dating. Okay. Yeah, exactly. We've already talked about this a little while ago because you guys are so far ahead of yourselves, but carbon-14 is a radioactive isotope of carbon, and it has a half-life of about 5,730 years. And this has been super, super popular in a lot of the sciences to help us figure out the ages of more recent things up to about 60,000 years ago. As long as it was something that was incorporating carbon from the atmosphere, we can date it, or at least date when it died. When you need to go farther back than that, you need to have isotopes that have a larger half-life. So uranium is a good one for that. With 4.5 billion years, you can if you have a rock that has uranium in it, you can date when that rock was formed. So it gets kind of interesting. How in the world do we detect all this radiation? There are multiple ways. We can use what's called a Geiger counter, which is probably what you're familiar with because in all the science fiction movies they have them and they're walking around and it's like click, 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 and it goes click, 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 a whole bunch. And you're like, oh my God, I'm dying of radiation. This is a Geiger counter that does that. This device right here that you see in front of you is a Geiger counter. It's awesome. I'm sure they make better ones today. But let me tell you, before we turn it on, see this one doesn't even have a speaker. It has headphones, so you can't make the clicking sound. And so you need to know how a Geiger counter works. Oh, I hate it when it does that. Here's how it works. Jonathan. You guys are having a rough class today. Here's how a Geiger counter works really roughly. Okay? It deals with the idea that radioactive particle like a alpha or a beta or even a gamma, when it comes through a gas, it will interact with some of the atoms in that gas and it'll tend to ionize them. It'll rip off electrons. The energy of it coming through will tear off electrons and create ions. Create little negative electrons, but also create little positive nuclei. So here comes my alpha particle right through this thing. And in here, it's created a whole bunch of ions, both positive and negative, as it's ripped off electrons of the atoms in here, okay? Oh, I don't know. Something. Could just be air even. If I have set this up electrically so that I've got some wires in here, and I've made this middle thing charged, let's just call it positive, and then the outer casing is negatively charged, but I think it could go either way. Okay, I put a potential difference in my little collector here. When those ions are created, they'll be attracted and repelled from one side or the other. So all these negatives will glom onto the positive, all these positives will move to the negative, and you'll create an electric current. An electric current will be in there, and then you have a device to sense that there was a little flash of electric current, and the device says, oh, cool, a piece of radioactivity just came through here. I'm going to count it, and then you can either measure it with a needle or a counter or make it go click every time that happens, and that's your Geiger counter. Okay? So the more particles going through, the more ions you get, and boom, the more clicks you get, and you know there's more radioactivity. Okay, second type of detector is a scintillation counter. Ooh, scintillating. Scintillation counter. And a scintillation counter is pretty darn neat. What does that scintillation or scintillating mean? If you have a substance that it's made of atoms that when a charged particle passes through, they will interact, and the electrons on the substance will get excited. Those electrons will jump to higher energy orbitals. They'll be excited, and when they drop back down, they'll give off a little photon of light. Okay, and if you can measure those photons of light, you can measure radiation. That's a scintillation counter. And